Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight I am very excited to be starting a new project which I am calling the Organic Chemistream, which as the name implies is a live stream in which we talk about organic chemistry. So I've been covering general chemistry off and on for over a decade now, and I've been asked by people over and over again, when are you going to start covering organic chemistry? And I keep putting it off because there's still so much general chemistry content to cover. But recently, I've decided that I think it's probably a good time to start covering organic chemistry. So I'm really excited about this, and I hope that you are as excited as I am. And I'm not sure if you've been paying attention to my channel at all, but recently I put out a poll on the community tab of my channel page. So I'll show you that poll now. So basically, it was just two choices. One, keep covering general chemistry, or to start covering organic chemistry, right? And as of the time that I checked the poll, 98 people voted, and many thanks to all 98 of you who voted. And the results are shown below. Okay, so you got 43% voted in favor of continuing to cover general chemistry, and the remaining 57% voted in favor of starting organic chemistry. And so with 57% of the vote, the voters who voted to start covering organic chemistry have successfully won me over. And so that's kind of why I'm choosing to do this, because I want to do what you guys want to do. I want to respond to your feedback. So again, since the majority of people voted for organic, that's what we're going to do. I got a message from Adiola Aziz, says, good morning from Nigeria. It's 2 a.m. here. Wow. Good morning. Good morning. It's actually 9 o'clock p.m. over here, eastern side of the United States. So thanks for watching. And that goes for all of you who are watching right now and all of you who will later be watching this as a video. By the way, for those of you who are watching now, I do have a Discord server, so you can call into the show. There's a link down in the description if you would like to call into the show. If you do call in, do me a favor and let me know in the chat that you're calling in, because I only have like 2 monitors, and I don't really have enough space to have my Discord window open at all times. So just do me a favor. And I don't have any moderators or anybody helping me out. This is kind of a one-man show. So if you do decide to call in, just let me know in the chat that you're calling in, and we can have a voice-to-voice conversation. I would love the opportunity to do that, as always. Historically, not a lot of people have taken me up on that, but nonetheless, that option is available. And if you're watching this as a video, please leave a comment, because as I'll talk about later on in this stream, your feedback is super important to me, and I want your feedback to determine the direction of where we take the stream, what topics we cover and how we cover them, and how much practice we do, and all that kind of stuff. All right, so tonight, basically what I want to do is just a very gentle kind of get your toes wet in the water sort of introduction. I don't want to lay on too thick with the content tonight. There's basically 2 things I want to do. First thing I want to do is to simply define organic chemistry, right? Very important that we're all on the same page with regard to the definition of organic chemistry, because if we're not all on the same page, then that might lead to some problems later on. So we're going to define organic chemistry, and we are also going to talk about some of the general chemistry topics that we really need to have under our belt. We need to have a rock solid understanding of several, not all, but several general chemistry topics. So we're going to talk about those. And then I think next week we'll sort of go into those in more thorough detail. But tonight, again, it's just going to be pretty casual, just a conversation, a gentle introduction to organic chemistry. So yeah, usually when it comes to introducing a new topic, I always like to the first thing I like to do is just define the topic. And so definition of organic chemistry, I forget where I pulled this from. I think it was from the American Chemical Society. I should have listed the source here on the slide, but I didn't. So this is the definition of organic chemistry. It's the study of the structure, properties, composition, reactions, and preparation of carbon-containing compounds. So carbon, right? Carbon is sort of at the root of organic chemistry. And you might be asking yourself, well, there's, over 100 other elements in the periodic table. What is so special about carbon to the point where we have big textbooks and semester-long courses devoted to the study of compounds that contain this one element? And the answer is that carbon is really, really, really versatile, right? You can do a lot with it. Carbon likes to form bonds with other carbon atoms. It likes to form bonds with non-carbon atoms like hydrogen and nitrogen and oxygen and fluorine, chlorine, bromine, iodine, all this kind of stuff. There are several molecules in which you have very, very long chains of carbon atoms joined together. And then off of those chains, you can have branches of carbon atoms with other stuff hanging off of them. Carbons can double back on themselves to form rings of carbon atoms, 4-membered rings, 5-membered rings, 6-membered rings, 18-membered rings. Just there's so many possibilities. So the fact that carbon is so versatile is what gives rise to a huge, like literally millions and millions of possible compounds containing carbon, each with their own unique properties, reactivity, methods of synthesizing them. I mean, the list just goes on and on and on. So this is why and also organic chemistry applies a lot to our daily lives, right? The food that we eat, the clothes that we wear, us, the macromolecules that make up living organisms, proteins, RNA, DNA, those kind of things, right? So organic chemistry, very, very big, very, very important discipline, right? So the next thing I want to show you guys is the textbook that I'm using. Now, I don't think it's super critical for you to necessarily know the book that I'm using. I mean, organic chemistry is organic chemistry. I don't think you're going to find anything in an organic chemistry book that's going to like contradict another organic chemistry book. It's pretty much all the same. And also, as I do these streams, I don't think I'm going to go, from front cover to back cover in any kind of like order of my textbook. I'm just kind of I'm going to kind of cover the topics as I see fit and what's logical, what's sensible. But nonetheless, you might be interested in the book that I'm using. This is going to be the book that I use, that I sort of like read off of and gather my thoughts and prepare for the live streams throughout the week. It's called Organic Chemistry. The author is David Klein. This is the 4th edition of the book. Offspring Freak says, yes, great book choice. Thank you. Yeah, this actually isn't the book that I used when I was studying way back in college. I used a book authored by a guy named John McMurray, and I really liked that book. So it kind of took a lot for me to abandon the McMurray textbook and go for the Klein textbook. But I've heard so much about this book. This seems to be like the most popular organic chemistry textbook. And so it makes sense for me to kind of, work off of this book as I prepare for these presentations. So if you would like to sort of follow along with the same book that I'm using, this would be the book that you want to find a way to get your hands on. But again, like I said, it's totally not necessary. Organic chemistry is organic chemistry. I just wanted to let you know, in the interest of full transparency, that this is the book that I'm going to be using. Offspring Freak says, I used McMurray in college as well. Yeah, and it was pretty good, right? I thought it was pretty good. And then later, I think maybe like 2 years or so after I took organic chemistry, they switched from McMurray to Klein. And it I noticed it because the Klein book was significantly more expensive than the McMurray book. But anyway, enough about the book. So let's move on. There's another slide coming up here that is pretty important to me. It's kind of, clowning around a little bit, just posting memes on this slide. But I really, really wanted to emphasize the importance of feedback. I really want the organic Chemistream to be feedback driven, to be community driven. I want to talk about what you guys want to talk about. Whatever topics you want to discuss in the stream related to organic chemistry, that's what I want to talk about, right? Not just the topic selection, but also, how much practice you want to do. Just literally everything that we can do in this stream. I want it to be tailored to what you, the audience, wants. And so to that end, I say, please lay the feedback on me. The more of it I can get, the better. If the stream sucks, let me know that the stream sucks. I mean, that's good, valuable information to have. I mean, if you think it sucks, I would also like to know why you think it sucks. Or if you think it's good, let me know. I mean, I want to know everything. I want to know what you're thinking. It is absolutely essential for the growth and improvement of the stream. and of this channel. So thank you. Amelia Rasmussen says McMurray is a religion for me at this point, to be honest. I don't know what you mean by that. You mean like you religiously refer to the McMurray textbook and you just say no to all the other textbooks? Man, maybe I need to reconsider the choice of the book and then go back to McMurray. I don't know, but okay, enough about books, and we're back on books now. Let's get off of that topic. So, all right, so we've defined organic chemistry. We know the definition of it. I have told you what book I'm using, and I have put a lot of emphasis on the fact that I really, really want and need your feedback to do a good job at what I'm doing, because I don't want to be wasting any of your time. I certainly don't want to be wasting any of my time. So I want to have a good stream, but I need plenty of good feedback from you. So let's talk about some of the general chemistry stuff that we need to have under our belt in order to sort of lay the foundation for a really good understanding of organic chemistry. So when it comes to organic chemistry, there are two main general chemistry topics that are going to be very, very valuable going forward with organic chemistry. And these are two very broad topics. One of them is atomic structure, and the other one is chemical bonding. So very, very broad topics. There's a lot of information within those two topics. So let's talk about it. Beginning with atomic structure. So these are just a couple of bullet points that I just kind of wrote up here. And there's probably other stuff that would be useful to know that's not included in this bulleted list, but I think this is like a good place to start, right? So by now, and again, I'm teaching organic chemistry under the assumption that you already have a decent understanding of general chemistry, but nonetheless, I think it's important to sort of revisit some of this stuff, because sometimes when you study things, you get really deep in the weeds, and you tend to forget about the basic underlying scientific principles that govern the behavior that you're looking at. So, okay, so atomic structure, right? By now, we know that an atom is composed of a nucleus and an electron cloud, right? Most of the mass, the overwhelming majority of the atom's mass and all of its positive charge is concentrated in a little teeny tiny, by volume, position in the center of the atom called the nucleus, and the rest of the atom's volume is taken up by the negatively charged electron cloud. And I'm calling it an electron cloud because the best, most accurate way to describe the behavior of an electron is to describe a region of space in which you are likely to find the electron. And we call those regions of space orbitals, which sort of transitions us into the next bullet point here. The quantum mechanical model of the atom. So this is the most contemporary, most current, most commonly accepted model of the atom that we use today. And I actually have an entire playlist. There's going to be a lot of links in the description, by the way. I probably should have mentioned this earlier on in the stream. But once I get around to saving this as a video, I'm going to put a bunch of links in the description that show you my playlists and my videos that go into more thorough detail about all these topics that we're going to talk about tonight, all this general chemistry stuff, right? So the quantum mechanical model of the atom, it's basically a manifestation of the electron behaving not only as a particle in the sense that it has like a definite mass and definite charge and stuff like that, but also that electrons behave as waves, right? And in behaving like waves, well, waves have some interesting properties where they build each other up. That's called constructive interference. And then in other situations, waves destructively interfere, meaning that they cancel one another out, right? And as a result of the wave behavior of electrons, you get these discrete energy levels, right? That's the big discovery when it comes to the quantum mechanical model of the atom, is that the energies of electrons are quantized. They are limited to certain discrete values, right? So when an electron gets promoted from one energy level to another, it doesn't climb up from one energy. It literally teleports. It just instantly jumps from one energy level to another. That was kind of the big discovery when the quantum mechanical model was first being proposed, right? And so as a result of all that, you have these things called principal energy levels. And then within principal energy levels, you have what are called sublevels. And sublevels are generally shown by letters, like the S sublevel with the S orbitals, the P sublevel with the P orbitals, the D sublevel, the F sublevel, and so on. And then within sublevels, you have orbitals, right? You have principal energy levels. Each principal energy level has a given amount of sublevels. Each sublevel has a given amount of orbitals. And again, I have videos. Just check the links in the description if you're watching this as a video, explaining all of this in very, very thorough detail, right? And so when we're describing what the electrons in an atom are doing and sort of where they are and how they're positioned within the atom, we use something called an electron configuration, right? So the electron configuration specifies which principal energy levels, which sublevels, which orbitals are populated by electrons. And the lowest energy electron configuration of an atom, that's what we call its ground state electron configuration, right? And so I have a video explaining how to build the ground state electron configuration of any element in the periodic table. Like I said, I'll be sure to provide the link for that video in the description. And then one important aspect of electron configurations is the concept of valence electrons, right? So valence electrons, those are the electrons that are located in the outermost principal energy level, the outermost shell, right? Shell is just kind of a synonym for principal energy level, right? So those valence electrons, those outermost electrons, those are the most important electrons that an atom has because it is the valence electrons that participate in chemical bonding, right? Chemical bonding is pretty important, right? And so electron configurations, valence electrons. One thing that's also important to point out is the stability of the noble gas electron configuration. So remember what the noble gases are? Those are all the elements in the rightmost group of the periodic table. Your helium, your neon, your argon, and so on and so forth. What the noble gases have in common is that their valence shell, their outermost principal energy level, is completely full of electrons, and there is a special stability, a special low potential energy situation that is achieved when you have a full valence shell. And so other elements in the periodic table, right, you can think of them as like jealous of the noble gases, right? They will, in the case of a metal, lose electrons, or in the case of a non-metal, gain electrons or share electrons with other atoms in order to achieve that noble gas electron configurations, right? And this is where things like the octet rule come into play, right? They call it an octet rule because the S and P sublevels together account for 8 electrons in the P block over here in the periodic table, right? So, but we'll get into we'll get into that in more thorough detail also later. Another very, very important property of electrons or of elements as another manifestation of the quantum mechanical model is a property called electronegativity. Electronegativity, very, very important property. Yep, I do have a video entirely devoted to electronegativity. And electronegativity, remember, is the tendency of an atom to draw electrons toward itself, right? And for reasons that I thoroughly discussed in my electronegativity video, electronegativity tends to increase as you go up a group of the periodic table and as you go from left to right. So the highest rightmost elements like fluorine and oxygen, those are the most electronegative elements. And then, you know, your metals on the bottom left-hand corner of the periodic table, like francium and things like that, those are the least electronegative. They have a very lousy tendency to attract electrons to themselves. Okay, so again, that's kind of the main thing that we need to know, or these are the main things that we need to sort of understand about atomic structure. So I want to ask you guys who are watching live right now, any of these bullet points, any of these topics, in your opinion, should we go over these things in greater detail? Because all of them are quite important, right? Very, very important, especially to understand electron configurations. Very, very important to understand valence electrons, noble gas configuration, and extremely important that we understand electronegativity. So if anything, if you're fuzzy on any of these topics and you think we should go into more detail, especially, let's say, after you watch my videos that I have on these topics, let me know. Leave a comment. I really want to know. So, all right. So that's atomic structure. And then the other broad general chemistry topic that we need to make sure we understand very, very well in order to take a crack at organic chemistry is chemical bonding. Let me move myself out of the way here. So make myself, whoops, let me change that. Okay. All right, so chemical bonding. So there's a lot of information in here. And again, I have videos on all this stuff. So it's kind of important to understand just the basics, right? So what is a chemical bond? Why do chemical bonds form, right? So chemical bonds, you can think of them as like the glue that sort of hold atoms together, right? And the reason why chemical bonds form, so a chemical bond is basically just a strong attractive force between atoms. And the reason why chemical bonds form, right? It all has to do, fundamentally, it all has to do with the tendencies of like charges to repel one another and opposite charges to attract one another, right? So we understand that atoms are composed of subatomic particles. The nucleus has the positively charged protons in it, and then the rest of the atom has the negatively charged electrons, right? And so there's all these different attractions and repulsions, right? You have the nuclei repelling of two atoms, the nuclei of two atoms repelling one another. You have the electron clouds of two atoms repelling one another, and then you have the electron cloud of one atom being attracted to the nucleus of another atom, right? So there's sort of like a happy medium, right? There's sort of a happy, and by happy medium, what I'm talking about here is the reason why chemical bonds form is because bonding lowers the potential energy of the atoms. The potential energy of atoms when they're bonded to one another is lower than the potential energies of those atoms when they're not bonded to one another. This is why chemical bonds form, because both chemical and physical systems tend to act in a way that minimizes potential energy wherever possible. Potential energy, of course, being the energy that is associated with the position or the composition of an object, right? So the classic example of like potential energy, you'd say something like this. So like I have like this battery that I'm holding up really high, right? This battery has a fairly large amount of localized potential energy because its position way high up in Earth's gravitational field, right? This physical system is going to minimize its potential energy whenever possible, which is why when I drop the barrier that holds up the battery, it spontaneously falls down, right? So, all right, I have a couple messages in the chat that I'm going to read. Let's see. Offspring Freak says, well said. I think touching on each one quickly is a good idea. Having visuals as you speak on them would be ideal, for me at least. Thank you for that. Kitty says, hey, organic chemist. Oh, welcome, Kitty. Nice to see you. Adiola Aziz says, I think you've given introduction already. Let's just move on, please. All right. Thank you. Yes, thank you for all that feedback. I appreciate it, right? So we know what a chemical bond is. We know why bonds form. It lowers potential energy. Ionic and covalent bonding, important that we understand that. Ionic is just the transfer of electrons, typically from a metal, which tends to lose electrons, to a non-metal, which tends to gain electrons, right? And the ionic bond is just the electrostatic interaction that takes place between those oppositely charged ions, right? Covalent bonding, as we know, is the sharing of electrons between two nonmetals. Also important that we understand the difference between nonpolar and polar covalent bonding, right? So the term polar covalent bond applies to a bond in which the two atoms that are bonded together have a large difference in electronegativity. That is, they have different tendencies to attract electrons to themselves, right? So a polar covalent bond has two atoms bonded together with a significant difference in electronegativity between them, which basically means that the electrons, although they are being shared between the two atoms, they're being shared unequally. The more electronegative element tends to hog up some more of that electron density within that covalent bond. And then if the electronegativity difference is very high, then you get a full-blown ionic bond where you have a complete transfer of one or more electrons from, like I said, typically a metal to a non-metal. And then finally, we're going to look at the chemical bonding theories that we talked about in general chemistry. Very, very important that we understand this, because a lot of the organic chemistry stuff that we're going to talk about in the coming streams is going to draw upon this knowledge, right? So one of them is the Lewis theory, which is kind of a primitive bonding theory, but we still use it today because it does provide a lot of value, right? So what does Lewis theory tell us? It basically just tells us within a molecule, which atoms are connected to which, and what's going on with the valence electrons. Are they participating in bonding, or are they lone pairs, as they called electron pairs that are localized on individual atoms within a molecule, right? And so with Lewis theory, we have Lewis dot structures. Very important that we're able to draw Lewis dot structures for individual atoms, and also that we're able to draw Lewis dot structures for simple, small molecules, right? So at this stage in your chemistry education, you should be able to, given the formula for a molecular compound, a simple, small molecule, you should be able to draw the Lewis dot structure for that compound, right? And within Lewis dot structures, of course, we have things called, formal charge, right, and resonance, and we're going to go through those more thoroughly too, because those are also very, very important. And then we also have valence bond theory. So valence bond theory, which includes the topic of hybridization, basically characterizes a chemical bond as an overlap of atomic orbitals, right? And then, so hybridization is kind of a big one that confuses a lot of people. So the basic idea behind hybridization is that you have atomic orbitals mixing together to form hybrid orbitals. And the advantage that the atoms enjoy when they form hybrid orbitals is that hybrid orbitals tend to overlap better with other atoms than just standard atomic orbitals do, right? So if you have a better overlap of orbitals, right, that's going to give you a lower potential energy, right? And so by forming hybrid orbitals, those central atoms like carbon can form more bonds to other atoms, and forming more bonds leads to a lower potential energy. And so you get, s orbitals, or you get the s orbital in the energy level mixing with p orbitals to produce hybrids, right? If you have one s orbital and three p orbitals together, that'll give you 4 sp3 hybrids. If you have the s orbital combining with 2 p orbitals, you'll have 3 sp2 hybrid orbitals. And then finally, if you have an s orbital combining with 1 p orbital, you'll have one sp hybrid orbital, right? That's valence bond theory. It's also pretty important, although perhaps not as important as valence bond theory, but it's also very important that we understand molecular orbital theory, right? So bonding and anti-bonding molecular orbitals. And again, I know I've said this several times already, but everything that is in this bulleted list, I have videos for all of it. So if you're watching live, I apologize. I don't have those links in the description, mostly because I kind of want you guys to stick around. Don't want you to click away. But if you come back after this is published as a video, all of that information, all of those links to all those videos that'll help bring you up to speed if you're a little rusty on these topics will be there for you in one convenient location. And then the last topic within chemical bonding that's really, really important that's on this list is molecular shape, which is governed by VSEPR theory, VSEPR, valence shell electron pair repulsion, based on the fairly simple idea that electrons being negatively charged are going to repel one another around a central atom to try to space whatever atoms are bonded to that central atom as far apart from one another. So if you have 2 electron pairs around the atom, you'll get a linear shape. 3 electron pairs around the atom, that'll give you a trigonal planar shape with a bond angle of 180 degrees, or 120 degrees rather. If you have 4 electron pairs around a central atom, that starts to, you start to go into the 3rd dimension, right? That results in a 3-dimensional shape, and that geometry is called tetrahedral, with a bond angle of 109.5 degrees. And then to get molecular geometry from electron pair geometry, you basically just consider the effect that removing one of those electron groups has. So in other words, let's say you have a tetrahedral electron geometry with 4 electron pairs, right? And if you were to sort of hide one of them, what would that resulting shape look like? Well, it would look kind of like a pyramid, so we call it trigonal pyramidal. So again, I know I'm kind of blazing through this pretty fast, but again, the reason why I'm blazing through this pretty fast is because this is all stuff that we should know well at this point. If you don't, then you can watch my content on it, or watch other content, or read up on it. I don't necessarily care where you learn the content from. But what I'm really afraid of is I don't want to start blazing through organic stuff, and I don't want you to get confused because you don't have a solid foundation of the necessary general chemistry knowledge that we need to study organic chemistry. So there it is, folks. So that is basically it. Like I said, I just wanted to provide a very, very gentle introduction to the topic of organic chemistry. And I think I did. I mean, like I said, it was a very gentle introduction. Obviously, one of you, Adiola, is, wants to just kind of move on and start getting into the guts of organic chemistry. I definitely understand being eager to do that. But like I said, I just wanted to do a very, very gentle introduction today. But I also, again, what I really want is to respond to your feedback. So what exactly, I just want to know more about you. Like, what are you studying right now? Are you in college? Are you taking organic chemistry right now? If you are taking organic chemistry right now, what are you currently studying? Maybe you're going to be taking organic chemistry soon, maybe in the summer or next fall or something like that. Really, I just want to know where you guys are at so that I can make content that's more tailored to you. So, all right, everyone, that is going to do it. This has been the introduction to the organic Chemistream. Next week, I'll do one of two things. I'll either go through those general chemistry concepts in more thorough detail, or we will just move right into the organic stuff, talking about probably alkanes and cycloalkanes and things like that. I also want to talk about, some of the organic chemistry conventions that you don't really learn in organic or in general chemistry, like the condensed structural formulas, using curved arrows to show the direction of electron flow within a reaction or within a mechanism, all of those things. So yeah, organic chemistry is kind of a challenging subject to teach because there's not really necessarily like a straight linear path to teaching it. There's a lot of ways that we could go about doing this. So that's kind of what I'm trying to figure out from you guys, is what you guys want to look at first, what you guys want to look at later. And to that end, I say, please leave me your feedback. Please leave a comment. And I would appreciate reading your feedback so that I can make a better decision about what to do for the next stream. All right, everybody. Love you guys. Thank you very much for watching. Really, really excited about this project. Like I said before, I hope you are as excited as I am. And I will see you in the next episode of the Organic Chemistry. Take care, everyone.